we talked about vector fields, and might be a reason for a line integral on a vector field. So let's just do one of those. Well, as you might imagine, it gets a little complicated. Not too bad, but okay. So let's say we start with a vector field. F equals some function of x, y, z. Call it p. We'll do 3 dimensions. Works similarly in 2 dimensions, of course. Okay. All right, so we've got a vector field. This is how the vectors are running in this particular case. All right. All right, then we have a, they usually do it in, again, in terms of do the curve in terms of a vector. Call it R. And R equals, in parameter t, x of ti, y of tj, and z of t, k. T runs A to B. But it turns out, what you're going to do then is the line integral this is how they usually write it. Vector field F dotted with dr, differential of R. Okay. So to actually evaluate this, and this, the example in the book it talked about was like if you have a gravitational field or forget the other one. Magnetic force field or something like that. This gives you the work done if a particle moves along the curve. Anyway, it turns out you do A to B. Then you take the vector field evaluated at your curve RT. Dotted with R prime dt. Yeah, so basically you got to plug in what R of t is into your vector field. You got to get the derivative and then do your integral. So it's kind of a three-step process. But it turns out, in the examples anyway here, it doesn't, the integral turns out not to be too bad. Of course, it'd be easy to get one. It would be pretty fun. Okay. So let's see. Let's need more space. So let me get my example written up here. Okay, so evaluate f dot dr, where let me do it this one. Where f of xyz equals xzi minus yzk. No j component for the vector field. And C is the line segment from -1 to 0 to 3, 0, 1. Okay, and so as we noted, we need an R of t, so we need this C in terms of a vector, R of t. And we just so happen to know how to do this. Now this is the three-dimensional version, but the three-dimensional version of the line segment is the same as the two-dimensional version. You take 1 minus t times R0 plus t times R1. Or in this case, R0 is just this negative 1, 2, 0 vector, and then R1 is that vector, 3, 0, 1. Okay. So we've got what? Negative 1 plus t, 2 minus 2t, and then 0, right? You multiply the 1 minus t times each component. And then this one is 3t, 0t. And so we wind up with r being negative 1 plus t plus 3t, so it'll be negative 1 plus 4t. 2 minus t plus 0, so it'll be 2 minus 2t. And then 0 plus t, so it'll be t. And so that's our r vector. Okay. So again, what we're looking at to do here is we need, remember this is going to equal f evaluated at r of t dotted with r prime t dt. So we are going to need, we can write it out here. Yeah, plug in, find f of r t. So basically we're plugging, x of t is that, y of t is that, z of t is that, into this. Right? So it'd be x, so it'd be negative 1 plus 4t, z, which is just t, I, minus y, which is 2 minus 2t, z, which is t, k. And so all that does, cleans up a little bit, I guess. Negative t plus 4t squared. I minus 2t minus 2t squared, k. There's no j component there. Then, so that's this part. And then r prime was easy. The r prime vector would be just the derivatives, right? So it'd be 4, negative 2, and 1. And then we need to dot those two things together, right? And so that's why they, anyway, this, one way to do it all separately so you don't have to keep up with all the parts. All right, so we get to do a dot product. Dot product, what do we do? Just add, multiply the components together and add them together. So we take this component times this, so that would just be 4 times the negative t, I'll write it out here, plus the j component is 0, so negative 2 times 0 would be the j component. And then minus 2t squared times the k component over here is 1. And so, yeah, this is a dot product, so it turns out to be, it's just a scalar, you know what I mean, but what do we got? Negative 4t plus 16t squared, that's 0. That would be minus 2t plus 2t squared. So we wind up with this dot product is 18t squared minus 6t. And so that's what we're going to integrate, isn't it? And then, of course, r of t, I forgot to note, comes nice and neat because it's just from 0 to 1. And so that's what we integrate from. All right, so let's get this where we can write this all down. Okay, so the integral of this vector field. So it's a to b, so we said it's 0 to 1. The dot product is 18t squared minus 6t dt. So, yeah, turns out the integral's fairly simple. Yeah. What would it be? 6t cubed minus 3t squared, 0 to 1. 6 minus 3, just 3.